You ever stop and wonder what actually holds soil together? You know, what gives it its life, its fertility, its power to grow pretty much everything we eat? Well, the answer is kind of hiding in plain sight, except it's way too small to see it all. We're talking about soil colloids, these microscopic glue-like particles that are the real unsung heroes of the world right beneath our feet. So let's get into it. All right, here's what we're going to cover. First, we'll break down exactly what these particles are. Then we'll get into their pretty unique properties. We'll meet the two big families, clay and humus. Then we're going to take a closer look at the silicate clays. And finally, we'll tie it all together and see why these tiny, tiny particles have such a massive impact on, well, everything. So where did this whole idea of soil glue even come from? Well, to really get a handle on these tiny powerhouses, we've got to go back, way back, like over 150 years to the very beginning of colloid chemistry. Right, so this guy, Thomas Graham, he figured it out with a really simple but kind of brilliant observation. He noticed that if you dissolve something like salt in water, it passes right through an animal membrane. Easy. But other things, they just didn't. They got stuck. He called these colloids, which comes from the Greek word for glue, because they were just suspended in the water, not truly dissolved. And that one little discovery, it basically kicked off a whole new field of science. Okay, so that leads us to the big question, right? What's the dividing line? What makes a particle just a particle versus one of these powerful glue-like colloids? Well, it all boils down to one thing: size. And when I say small, I mean incredibly small. These particles are so minuscule, you literally need an electron microscope just to get a peek at them. And here's the kicker. It's that tiny size that gives them a ridiculously huge surface area compared to their volume. To give you some perspective, just 1 gram of clay colloids can have a surface area bigger than a football field. That right there is the secret to their power. So, what does having all that surface area actually do? Well, it leads to some very unique and very important behaviors. Let's take a look at the key properties that really define what a colloid is. Okay, so if you suspend these guys in water, they're constantly being bombarded by water molecules, which makes them dance around in this random, zigzag pattern called Brownian motion. They also scatter light. You know how you can see a sunbeam cutting through a dusty room? That's the Tyndall effect. But most importantly for soil, they have the power of adsorption, cohesion, and adhesion. They stick to things. But there's one property that rules them all. All right, if you remember one thing from all of this, make it this. Soil colloids have a net negative electrical charge. This single fact is the key to pretty much everything they do. It turns every single one of these tiny particles into a little magnet for positively charged ions. And it just so happens that a lot of those ions are essential plant nutrients, like calcium and potassium. Now, not all colloids are created equal. In the soil, they basically fall into two major families. You've got the inorganic mineral ones, which we all know as clays, and then you've got the organic colloids, which we call humus. So clays, they're born from rocks weathering down over thousands and thousands of years. They're crystalline, mostly made of silicates. Humus, on the other hand, is what you get at the very end of decomposition, that rich, dark organic stuff that's left after microbes have done their thing. Now, they both have that all-important negative charge, but humus is super negative. That makes its ability to hang on to nutrients just, well, exceptional. Let's zoom in for a second on the most common type of inorganic colloid, the silicate clays. Because this is where you can really see how their microscopic structure completely dictates what they do in the real world. So how in the world does a mineral crystal end up with a negative charge? Well, one of the main ways is this process called isomorphic substitution. Think of it like building with Legos, but you accidentally swap in a piece that looks almost the same but is just a little different. As the clay is forming, maybe an aluminum ion, which has a 3+ charge, sneaks in and takes the place of a silicon ion, which has a 4+ charge. The size is right, but the charge is lower. That tiny little swap creates a permanent negative charge in the whole structure, turning the entire clay particle into a tiny nutrient magnet. And this is a perfect example of how structure equals function. Look at kaolinite. It has a simple, stable, one-to-one layered structure. That means it doesn't swell much, and it has a pretty low capacity to hold nutrients. But then you get to Montmorillonite. It's a 2-to-1 clay, and water can wiggle its way in between those layers. So it swells up like a sponge when it gets wet, and then shrinks like crazy when it dries, causing those huge, deep cracks you sometimes see in the ground. Illite is also a 2-to-1 type, but it's got potassium ions holding its layers together a bit tighter, so it's kind of the middle ground between the other two. Okay, we've been deep in the weeds of the microscopic world. Let's pull back out now and see why any of this actually matters on the big scale for the soil we walk on and the food we're trying to grow. It's simple, really. Because of that negative charge, colloids are the single biggest factor in a soil's fertility. They latch onto positive nutrients and stop them from just getting washed away by the rain. Their giant surface area holds on to water for plants to use later. They basically act like rechargeable batteries, storing up a reserve of nutrients that they can swap with plant roots whenever they need them. And of course, that glue-like quality binds sand, silt, and clay together, which creates good soil structure and stops erosion. We've spent a lot of time on clay, and for good reason. But we can't forget about its organic cousin, because when it comes to holding and swapping nutrients, humus isn't just good, it's an absolute superstar. So just how much more powerful is humus? We measure this with something called the cation exchange capacity, or CEC. A really high-activity clay like that Montmorillonite we talked about might top out around 100. Humus? It can hit a staggering 150 to 300. It is, by a long shot, the most powerful nutrient and water reservoir in the entire soil ecosystem. And that is exactly why adding organic matter is so critical for healthy soil. So there you have it. The entire structure, fertility, and water-holding capacity of our soils, it all rests on the shoulders of these invisible giants. They are the engines of the ecosystem right under our feet. And that leaves us with one final and really important question. Since we know the very life of our soil depends on them, what can we do in our farming, our gardening, and our land management to protect and nurture these vital colloids?